Hey everyone, today I've decided to do a short video on a question on probability and counting principles. So let's go right ahead and start with the question. So first question says, Veli and Bongi are learners at the same school. Some days they arrive late at school. The probability that neither Veli nor Bongi will arrive late on any day is 0.7. So this means that this 0.7 is for them being on time. Okay. Now the question 1.1 says, calculate the probability that at least one of these two learners will arrive late on a random selected day. So my understanding of that is the probability of V for Veli being late or the probability of B for Bongi being late. So that's what we need to calculate. Okay, let's go on to the next question. The next question says the probability that Veli arrives late for school on a random day is 0.25, while the probability of both of them being late on that day is 0.15. So using this information, we must calculate the probability that Bongi will arrive late on a school day. Okay, interesting. We'll see how that works out. And then number 1.3. The principal suspects that the late coming of the two learners is linked. The principal asks you to determine whether the events of Veli arriving late for school or Bongi arriving late for school are statistically independent or not. What will be your response to him? Show your calculations. Nice question. All right, let's see how to approach it. So 1.1 only wants the probability that at least one of them is late. So to do this, we'll first draw a Venn diagram. Okay, so we'll have two circles to denote the occurrence of these two events. We'll name the first one V for Veli's lateness and B for Bongi's lateness. So now the statement here, as I said before, means that we are negating their lateness, both of their lateness. So it's the knot of their union. So it means this is outside the two circles. We want to know what the inside will be, because the question here wants to know what the inside will be. At least one of them means either Bongi is late or Veli is late, or both of them are late. So we want the numbers that are in here and add them together to give the answer. But even though we don't have enough information yet, we can still find out what the total of these three regions will be, because we know that this one is the one that is the outside number. So the knot of the union is outside the circles. So now there's a rule. So at least one of them, the rule that says P of A is 1 minus P of not A. So if we have the knot of the union and we want the union, it means we just subtract this one from 1. So this is what we'll do, and then we get 0.3 as the answer. That is the final answer of the probability of at least one of them being late. That is 0.3. Okay, next question. Next question says Veli and Bongi are learners. Oh, let's not start over there. 1.2. So the probability that Veli arrives late for school on a random day is 0.25. So This is probability of V. Then, while the probability that both of them arrive late for school is 0.15. Now, the 0.25, we could not do anything with it. We cannot put it anywhere because it is actually the number for the whole circle V, the two regions combined. But this one, so let's put this one over here. This one, the 0.15 is the intersection of the two. So that's when both of them are late on that day. So this is this region. So it means we can take that number and put it over there. Then let's bring this one here. Now I'm being putting these ones together so that we see we need to subtract these two in order to find this part. So it means we must minus 0.25 with 0.15, and this gives us 0.1. Okay, then now we only have one region remaining that we don't know. So this means that we can add all these things. So this is 0.25 plus 0.7, that is 0.95. This means that this one has to be 0.05 to make 1, because every region, when they're added, they must give you 1. So it means now we can now answer the question. They wanted the probability of Bongi arriving late. So we want everything that is in the circle of Bongi. So we must add these two numbers. And then that will give us 0.2. So that is the answer to that one. Next one, 1.3. So the principal suspects the late coming of the two learners being linked. So now we have everything we need in here. We need to just multiply the probability of V and B and see if it's the same as the intersection, because for independent events, probability of V and B is equals to the product of probability of V and the probability of B. So the probability of V and B is already given here. We found it to 0.15. Then the probability of V times the probability of B will be, we've taken these two numbers and added them. So this is the probability of V. And then we add these two as well. That's the probability of B. So these two adding together to give us 0.25. These ones give us 0.2. Then we multiply those two numbers and then we get 0.05. Now we check if these two things are equal, but they are not. 0.15 and 0.05 are not the same thing. So the probability of A and B, V and B is not the same as the probability of V and the probability multiplied by the probability of B. Now, how does this affect our solution? What will we tell the principal? The principal would be told that the two events are not independent. So if two events are not independent, it means they're dependent. So yeah, so it means maybe Bongi and Veli are making each other late, or they wait for each other maybe when they're late. I don't know. Next question about counting principles. So this one says the cards below are placed from left to right in a row. So we have 2 of diamonds, 10 of hearts, 9 of diamonds, 4 of hearts, 7 of hearts, and 8 of diamonds. So we notice that we have 3 of each suit. We have 3 diamonds and 3 hearts. Okay, so the first question says, in how many different ways can these cards be randomly arranged in a row? Okay, the second one says, how many different ways can these cards be arranged in a row if diamonds and hearts are placed in alternating positions? Okay, Then these cards are randomly arranged in a row. Calculate the probability that all the hearts will be next to each other. Interesting. Okay, let's see how to approach these ones. Okay, so the number of ways we can arrange n things is n factorial. So here we have 6 different cards, which means we're just simply going to take the 6 factorial, then that will be the answer. The answer is 720. Next question. How many different ways can these cards be arranged in a row if diamonds and hearts are to be placed in alternating positions? So I have a nice animation to explain this one. So we have 6 places to place all these cards. Then we can either have this configuration: D first, diamond first, then a heart, a diamond, a heart, a diamond, and the last heart. So this is one way this can be done. But remember, the D's are not the same and the H's are not the same. So, but always, if we started with diamonds, it would mean that we'll look at how many possible solutions, how many possible diamonds can we put here for first position, and then after we've placed that one, we'll see how many we put here, how many are left to be able to be put here, and so on and so on. But then there's another configuration of these D's and H's. We can have this situation where the H's are in the first position, the third, and the fifth position. Then again, remember the H's and the D's are not the same. So I should have labeled them H1, H2, and H3. So it could be H2 here, H3 here, and then H1 there. And so that's the number of different ways that these things can be placed around. So in order to solve this, we will do this. We will say that if we start with H's, there are 3 possible H's or hearts that I can place here. I can either put a 10 of hearts here, a 4 of hearts, or a 7 of hearts. But once I've placed that 4 of hearts, it means I have 2 left to place here at that position. And then once I put the second one, it means I have the very last one to put here of the hearts. And then again, the same for the diamonds. 3 diamonds at first that can be placed here, 2 diamonds here, and then 1 last diamond there. Then we take these, we multiply them together. And then this gives me an answer of 36. But now you must remember that we said there are 2 ways this can happen. We could have started with the blue D's. So it could have been blue 3, red 3. So it means there are 2 ways that we just showed. So it means the final answer will take that 36 and then we multiply it by 2, and then the final answer will be 72. Okay. Okay. Then this one says, if these cards are randomly arranged in a row, calculate the probability that all the hearts will be next to each other. Okay. So again, we have our 6 spaces, and then I've made the first arrangement that we can think of. So this is when the first 3 spaces are occupied by the hearts, so they're together. Now, it means wherever the next arrangement, wherever the hearts will be, there'll always be 3 hearts close to each other, but they could be between the D's like this. So as you can see now, this is another arrangement. So which means the hearts can be in between D1 and D2, and then again between D2 and D3, where D2 moves to the other side. And the last way, they could be at the end where D1, D2, D3 are starting, and then we have the hearts at the end. But remember, even the Ds themselves can move around. It could be D3, D1, then the hearts, then D2 at the end. And so those are all the different arrangements. So we're going to look at this as one thing, as a group. So this group is going to be counted as one. So we have one, and then 2, 3, and 4 things that are moving around. So because there are 4 things moving around, it will be 4 factorial. But remember, we also have a situation amongst the hearts themselves that they could also move around like this. So it could be a group where it's 1, 3, 2, the order of the hearts, and then they're again moving around between the Ds. So because of that, because there is movement amongst the hearts as well, we need to multiply by how many they are factorial. So the 4 factorial for the Ds and the group of hearts, and then 3 factorial for the hearts themselves. So the number of arrangements in total becomes 4 factorial multiplied by 3 factorial. Then the probability will be just taking what we got and divide by the total number of arrangements that we got in the first question, 2.1, that's 6 factorial. Okay, then to simplify this quickly, you can say 5 factorial, and then the 3 factorial is 6. Then I split the 6 factorial into 6 by 5 by 4 factorial. Looking at the 5 factorial, and this one will cancel out, and then the 6 and the 6 will cancel out. Then we end up with 1/5 is the final answer. Like and subscribe and press the bell notification button for YouTube to notify you when I've uploaded another video. I'll see you in the next one. Bye bye.